Good morning, professors and fellow students. Welcome to our final thesis presentation. Our group consists of Ahmad El-Rouby, Andrew Khalaf, Areeg Mostafa, Fady Mohamed, and myself, Nour Ghaly. Our thesis project is supervised by Dr. Amr El-Kadi and Dr. Karim Sobh. This is the agenda of today's presentation. Let us begin our presentation by discussing the problems that initiated this thesis project and the research questions that we are trying to tackle. The main problem that our project is trying to address is that general-purpose operating systems were not designed to cater for big data needs. General-purpose operating systems are just designed to give average performance on a vast range of application profiles. There are two fundamental issues that we're trying to tackle when it comes to big data needs, one being scalability and two being performance. Let us now move on to the research questions. We looked at several operating systems that are closely related to the research topics that we are trying to address, and here we discuss only a few of them due to time constraint. Cori exokernel is one of the operating systems that we studied. It is a distributed operating system. However, its drawback is that it is not asymmetric, which does not enable it to have specialized core roles, such as having a tickless working core. And by tickless, we mean that the timer is disabled, and therefore there will always be unnecessary interrupts. Amoeba is a general-purpose operating system which achieved the generality of a non-distributed operating system in a distributed environment. However, this generality will not be optimal for big data, as we have discussed. NileOS, which was built on Linux, is an asymmetric microkernel which is tickless. However, it is not distributed, and as the name indicates, big data is an extremely large amount of data that is required to be stored and processed, and hence this cannot be done on just one node. Therefore, a distributed environment is a must. Therefore, we needed to research and come up with a new microkernel that caters for all the research aspects that we just mentioned. And hence, the problems that we just addressed were the motivation behind our solution that we present to you today. NileOS, a distributed asymmetric tickless microkernel for big data processing.
From the very start of our project, we set up some goals that acted as a blueprint whenever we had to make any design decision. So let me remind you of some of the goals that we had in mind when designing the bare metal layer phase of this project. As a start, we wanted to reduce overheads, but not at the expense of extendability. We also wanted to minimize interrupts on big data tasks, and even try to eliminate them if possible. Also, we wanted to have cores as the fundamental building block of the system. Additionally, we wanted the ability to have or assign specific tasks to specific cores, whether remote or local, transparently. Finally, we wanted some sort of a programming model in which services can be added to the microkernel without needing to know much about the underlying architecture.
Now we're going to talk about the system's architecture.
This is our overall architecture of NileOS. Considering our distributed nature of the operating system, we have came up with a special control protocol called the IPloE, which stands for Inter-Processor Interrupts over Ethernet, for communication between nodes using extensible messages. This way we can avoid the deep network stack, as will be explained in detail later. As for each node, the cores communicate locally through the local IPI using extensible messages also. Each core in our operating system has a role depending on the type of interrupts it handles. For example, the disk core role handles the disk I/O interrupts. In general, we can have by minimum 2 cores in one node, one as a management/disk/network core, and the other one as a processing core that will receive interrupts only when necessary, as decided by the management core, as it must remain tickless. It's also notable to mention that each core has its own single address space and kernel/user stack. This is our microkernel architecture. At the bottom, we have the hardware layer consisting of the disks, RAM, network card, and any other hardware device. Our microkernel backbone is the service transport layer, short for STL in the kernel mode. It abstracts any hardware interaction between the user and the devices. The user simply issues a command to the STL in the user mode, and if it needs a kernel service, it forwards it to the STL in the kernel mode. This minimizes the overhead incurred by switching to the kernel mode. Next, we will give you a short, deeper insight on the service transport layer.
I am sure you have seen this multiple times, but let's recap on the backbone of our microkernel. We call it the Service Transport Layer, STL for short. Services are registered to the STL and can be called by name through a unified API called dispatch kernel. And the STL handles the context switch from user mode to kernel mode only if deemed necessary, such that services in user mode can invoke other services in user mode as well without doing a context switch to kernel mode, thus removing some overheads. And if the service needs privileged access, the STL in the user mode forwards the request to the STL in the kernel mode in the form of message passing, which will be further elaborated on in the couple of slides next. And to make the lives of future developers easier, we have developed a preprocessor that uses special tags to parse the file and separate functions that should run in user mode and those that should run in kernel mode. It also creates a library file that handles the registering of the new user services with the service transport layer, making the service deployment a much easier task, thus ensuring that future developers don't necessarily need to know much about the underlying architecture of the system.
And now for our progress in the thesis 2. We were able to finish setting up and configuring two network drivers, the RTL8139 driver and the E1000 driver for the Intel i217 chipset to send and receive packets, allowing our microkernel to access the internet. We have also implemented the ARP protocol, short for Address Resolution Protocol, that translates MAC addresses to IP addresses and vice versa. We have also implemented ICMP over IP to be able to ping the machine. And here's a quick demo for our microkernel processing the ping requests. Okay, so on the left we have NileOS, which we will be pinging to. Usually, since our IP address is not stored in the ARP table, the first packet will be an ARP request, which NileOS will reply to with its own IP address, and then afterwards ICMP packets can be processed. As you can see on the left, the first packet is an ARP packet, and then they are followed by ICMP packets. The XML service is simply an XML parser that allows us to parse the XML found inside the configuration files, as well as XML strings that will be used for message passing. However, the question of how will the services be able to know the method signatures of other services arises. And our solution to that is by having every service expose a special function called the discovery function, which is basically the schema of the service that any service developer has to use to invoke that service. We also have a generic function that service developers will utilize to return their results in the form of XML. As can be seen here, we have a service called the Ackermann's function to simulate heavy computations inside of our microkernel. The root tag is the service's name, followed by its functions parameters, and information about each parameter, whether it should be encoded, encrypted, its type and size, etc., allowing for maximum extensibility and portability.
From the beginning, one of our important design goals was to allow services to invoke any method in an extensible and transparent manner, abstracting all information about the physical location of this method. To do this, we have considered a message passing mechanism between all services and their methods. This mechanism enables us to integrate any service easily and without the need to understand or know the underlying information about the system. All messages exchanged between services are in XML format to allow for extensibility of these messages, giving service developers the freedom to implement the methods with minimal restrictions. Given that the building block of our distributed operating system is the core, we needed a way to allow different cores to communicate together. Luckily, this was already available within a single node. This was achieved by sending interprocessor interrupts IPIs from one core to another and by allowing these cores to exchange the extensible messages over shared memory. However, due to the distributed nature of our operating system, we needed the ability to exchange these messages beyond the limits of a single node. It's also important to note that local IPIs are guaranteed by manufacturers to be delivered. We wanted to achieve the same thing with messages exchanged across nodes. Our first thought was to rely on the traditional network stack and use TCP, for example, to exchange these messages. But we wanted to push these down even further. We designed a network protocol that allows us to achieve the reliability of high-level protocols without the need for a deep network stack that would slow down this whole process. So what is IPloE? IPloE is a network protocol that allows for communication between different cores across a network. It's a special protocol that was designed as a control protocol, which entails that it is not meant for data transfer. Its job is to coordinate and manage jobs or tasks across the system in a very efficient and reliable manner. IPloE uses extensible messaging in XML format to unify messages sent both within a single node and multiple nodes. Here's a diagram that might help us illustrate how all of this fits into our operating system. Let's take, for example, these two nodes, one of which wishes to invoke a method that belongs to another node. However, processing cores are unaware of any of the physical locations or the process it takes to invoke that method. And that's the way it works. Processing core on node 1 tries to invoke a method through the service transport layer, which then decides that this method needs to run on nodes 2 processing core. It encapsulates the method invocation parameters in XML format, sends it over to the network core through another extensible message requesting an IPloE invocation. The message is exchanged over the network until it reaches the network core on the other node. It decodes the message, forwards it to the other processing core, allowing it to execute the desired method as requested. To illustrate the design of the protocol, here is an overview of the IPloE header. First, we decided to have a general header that encapsulates the most important attributes and allow for dynamic header lengths, depending on the operation and to allow for future updates. Attributes include the protocol version, the header length to allow for dynamic headers, opcode which determines the operation, data length to avoid having fixed size packets, message ID and checksum to ensure the reliability and avoid corrupted packets. Finally, we have the flags field, which currently includes encoded and encrypted flags and allows for adding other flags in the future. A solid example for the protocol headers is the request header, which includes all the information mentioned earlier, along with the service and the method numbers we wish to invoke. It also contains the source and destination cores for this packet. The reply header, on the other hand, contains almost the same information as the request one, except for the method number, since we don't really need this in the reply packet.
The registry service is run by management cores and is responsible for keeping record of the cores irrespective of their location, whether local or remote. Since it's handled by the management cores, it is guaranteed that there is at least one registry service running per node. The Registry Service utilizes the Gossip Service to collect data about the environment resources. Therefore, when the cores join or leave, the Registry Service can be updated dynamically at runtime. A table is maintained by the Registry Service that contains the naming scheme of the cores as well as each core role. The Gossip Service is responsible for collecting gossip messages and forwarding them to the Registry Service, as well as sending gossip messages. To eliminate network contention and overhead, not everything is being broadcasted. Rather, only important events that inform the Registry Service about the availability of resources. When information is shared with one node, it then shares this information with other nodes, which decreases broadcasting as a whole, and hence the main benefit of using Gossip Service is to minimize network traffic. A gossip message is sent based on some criteria, and in our case we chose one of these criteria to be when two cores communicate, i.e. when a core invokes a service in another core, the Gossip Service sends a gossip message to it. The only time a Gossip Service sends a broadcast is when a node is up for the first time. This is a scenario which showcases the events that occur when a node gets up for the first time. As soon as the node is up, it has to inform the management core on it that the node is up. The management core then sends information about this node to the Gossip Service using local IPI. The Gossip Service then broadcasts this new information to the network cores of all other nodes using IPloE, and this is the only time a broadcast is used in the Gossip Service, as we have mentioned. Each network core then parses the information that was sent in an extensible message sent with the IPloE, and finally the parsed information is sent to the Registry Service using local IPI.
So you got to be wondering, if the IPloE packet is in the network layer to allow for fast processing, how can it go outside of the LAN? Here comes the IPloE gateway solution, which when forwarded a packet to along with the destination's IP address, it will encapsulate it inside of an IP packet, send it to the destination LAN's IPloE gateway, which will take the IP packet, process it, and get the IPloE packet to the correct node inside of that LAN. Notice how there is a gossip server inside each LAN to know the resources that the system has, whether it's local or remote. An application for the IPloE is using it to implement a client-server model where the client core can issue a GET request using IPloE to the server core and then sleep. The server core will then reply with a wake-up signal along with it an extensible message in the form of XML for the client core to resume its job.
This is our overall progress for this phase, and as a conclusion for 492. In Thesis 1, we have managed to get our kernel backbone up and running with basic mechanisms. As for Thesis 2, we have added extra complexity by reading files from the disk, having the cores communicate locally and over the network, as well as providing means to have user mode services. And here we present our 14 services that we have implemented and are all fully functional. Next, we have the overall demo showing our system as well as the IPloE.
For the demo.
In this demo, we would like to show you how the IPloE is used to invoke remote services or remote methods within a service on a remote nodes. So in this example, we have an acronym service which basically does heavy computation. It takes two values, the first value and the second value, and we do that computation in a loop to make it even harder. It's full of recursive calls. And here's the implementation of the acronym service. As you see, it's full of recursive calls as mentioned. Now we're going to use the node on the right to issue a request to the node on the left to do the heavy processing, and then it should return the value. Keep in mind that the node on the right is kept blocked until the processing finishes up on the node on the left, and then the value should be displayed. Now see, the processing happens on the left, and then the result is returned to the node on the right. As we conclude 492, allow me on behalf of our group state that our thesis project's main target was to research, design, and implement a microkernel-based operating system, the infrastructure with inherent support for extensibility, supporting policy enforcements, as well as the distribution of both resources and services. We believe that we have achieved this target, and we wish future engineers and next phase developers all the best of luck. Finally, we extend our deepest appreciation and sincere gratitude for Professor Karim Sobh and Professor Amr El-Kadi for their continuous support and help. Thank you so much.